Hi, I'm Norman Wahlberger. Today we're carrying on with this second part to this course in universal hyperbolic geometry. The aim in the second part is to bring a number of different geometries together. And we're starting out by having a look at spherical and elliptic geometries. That's what we will be talking about today. We'll talk a little bit about latitude and longitude. I'll talk a little bit about the history of spherical geometry and some of the contributions of the ancients. We'll discuss a little bit of basic trigonometry associated to the sphere, and then I'll get to introducing elliptic geometry as well. Okay, so I've mentioned before that our study of the sphere historically is very intimately connected with astronomy, with people trying to understand what's going on with the night sky. And for that, the crucial fact is that the Earth is rotating about its axis once a day. So every day it makes a full revolution about its axis. So if here is our physical Earth, and there's perhaps the North Pole and the South Pole, so this is the usual equator, then what happens is that the Earth is rotating around like this. It's a steady rate and goes around once every day. And that's why the sun rises in the east and sets in the west, because wherever the sun is, let's say the sun happens to be over there, then if you're over here, it's nighttime because you can't see the sun, and as the thing rotates, well, at some point you just start to see the sun over the horizon, and that'll be in the east direction. Okay, and then as you keep rotating, then you get to be midday, and then eventually the sun disappears from your view, and that's nighttime again. Of course, the Earth is a little bit tilted in its relation to the sun, and that there's also this secondary motion of the Earth going around the sun, which adds the seasons. So there's actually two rotations going on. The rotation of the Earth about its axis once a day, and the rotation of the Earth around the sun once a year. For astronomical purposes, the first rotation is the most obviously important one, because it means that as we look in the night sky, everything is rotating. And it's doing so at a uniform rate. That means that the notion of angle is almost forced upon us, because the angle is proportional to the time spent in a rotation. So it makes sense to divide, say, the equator into equal segments, each corresponding to an equal amount of time. For example, an hour. In an hour, the Earth moves a certain amount, or a minute, or a second. And the Babylonian system that we currently use for angles, going back 3,000-4,000 years before Christ even, is this one here, based on 360 degrees, on dividing the circle into 360 equal units, called degrees, and then subsequently dividing each of those degrees into 60 units called minutes, and dividing each of those 60 minutes into 60 seconds. So a rather fine subdivision of the circle. In this picture, if that's, say, 0 degrees, then that'll be 90 degrees. That's a quarter turn. And then a half turn is 180 degrees. 3/4 turn is 270. And with 360, we're back to where we started. So the ancients took this Babylonian scale and applied it to understanding the celestial sphere. So here's an example of a sphere, and on it we have two different kinds of lines drawn as a kind of reference coordinate frame. We have lines going from, say, the North Pole to the opposite South Pole, which would be just a little bit around the other side. And these are great circles because they're going through the center of the circle, the plane. So we have all these great circles, and they're equally spaced around the equator. They're called lines of longitude. So those are lines of longitude that separate the Earth into these equal strips. Each strip looks just like every other one. And these lines of longitude are convenient for explaining how far east or west we are from some reference point. So if we rather randomly assign, say, this line to be our baseline, then we can describe other lines of longitude with reference to that one. Perhaps 10 degrees east, 20 degrees east, 30 degrees east, and so on all the way around. Or if we're going in this direction, we could say 10 degrees west, 20 degrees west, 30 degrees west, and so on. Now these days, if you actually look on a globe of the Earth, then this zero line of longitude goes through Greenwich, England, which is rather randomly chosen to be the sort of central line. But there's something rather random about that. So the lines of longitude are naturally in correspondence with the rotation of the Earth. And they're a very natural thing to consider. When you look at a sphere on like a globe, you also see these other lines. They're called lines of latitude. And they are somewhat less natural than the lines of longitude. So the lines of latitude are also what we get by looking at angles. So somewhere inside the sphere is the center. And if you look at the center, a line from the center, say, to this reference point, and then go up an angle, then you are on one of these lines of latitude. So this line of latitude, let's say it happens to be 15 degrees, means that every point on here subtends an angle of 15 degrees with the equator. If you're at the center of the sphere and look up, you have to go 15 degrees up to go from the equator to this particular line. It's actually not a line, it's a circle in the sphere, but it's not a great circle. It's what we get by cutting it with a plane which is not going through the center of the sphere. So that might be 15 degrees. We'll say it's 15 degrees north because it's in the northern part of the sphere, the northern hemisphere. And then maybe the next one might be 30 degrees, and then 45 degrees, and so on, all the way up to 90 degrees for the North Pole. And correspondingly, in the southern hemisphere, we could measure, say, 15 degrees south, 30 degrees south, and so on. So then we have these basically two angular measurements that can describe positions on the sphere. First of all, longitude in this direction and latitude in this direction. So it's standard to write the latitude component first. So this point here, for example, would be 15 degrees north because it's on this latitude line, which is 15 degrees north. And it's 40 degrees west because it's on this longitude line, which is 10, 20, 30, 40 degrees west. This point B here, well, its latitude would be, say, 45 degrees. It's on that meridian line there, 45 degrees north. And in terms of longitude, 1, 2, 3, 4, 5, we're going over 50 degrees east. So on a map of the world, you will see lots of coordinates like this, latitudes and longitudes, describing the positions of points with respect to a reference frame that's created essentially by the ancient Babylonians. The idea of longitude being an angle of rotation in this direction, and latitude being an angle from the horizontal plane of the equator. So it's important to remember that to the ancients, a picture like this would have been very familiar, but it would not have been recognized as a picture of the Earth. It would be recognized as a picture of the celestial sphere. So the ancients had this idea in mind that this represented the sky around us. The sky above us is a sphere, and on it are stars. So to them, these points A and B would have been stars, and they would be able to draw constellations, different stars and their various positions. And they could also then record the motion of the planets on this sphere, indeed also the motion of the sun on the sphere as well. So the idea of this representing the Earth is a much more modern notion, because for a long time the ancients didn't have a very good idea about the geometry of the earth. They only knew their own little neck of the woods. But the large-scale structure of the earth and how it looks is a relatively recent addition to our knowledge. All right, so we see that the study of spherical geometry historically was intimately connected with the study of astronomy. And in fact, mathematics and astronomy were for many years almost the same thing. To the ancients, there would not have been much of a difference. All mathematicians were interested in astronomy, and all astronomers were mathematicians pretty well. Now, the story of the history of the astronomical aspect, and especially related to trigonometry, is told in a very nice book called The Mathematics of the Heavens and the Earth, The Early History of Trigonometry, by Glenn van Brummelen. And if you're interested in a bit of history and with some interesting mathematical connections, ancient Greeks, Hindus, Arabs, this book is to be recommended. So the ancient Greeks had a lot of mathematicians who contributed to astronomy and to the study of the sphere, including Archimedes, Hipparchus, Theodosius, Menelaus, Ptolemy, and quite a few others. That were ranged from 300-400 before Christ to 200-300 after Christ. The Indian mathematicians, starting with the years roughly 500 AD, going up to 1100, contributed also a great deal to astronomical observations and theoretical mathematics for it. So we have mathematicians Aryabhata, Bhaskara 1 and 2, there are two Bhaskaras, Brahmagupta, Madhava and his school in Kerala, and again, no doubt many others. And then a little bit later, the torch was passed to the Arabs, Persians, and we have many notable achievements and developments, further refinements of trigonometry, especially in the spherical case. And names, probably I won't be able to pronounce them correctly, Abul Wafa al-Bujani, and then al-Biruni, al-Kashi, al-Khwarizmi, al-Jayani, and many others too. Al-Khwarizmi is a very notable mathematician who gave us the name algorithm and algebra, in fact, also. So a lot of contributions, a lot of study of the sphere in the context of astronomy, and the trigonometry that we now learn in schools almost invariably arose in the spherical case first, because that was for millennia clearly more interesting and important than planar trigonometry. And it's curious that modern students are almost universally completely ignorant of this fact. And spherical geometry is some kind of relic from the distant past, which many students will go even through an undergraduate education and not learn any spherical geometry. It's a bit remarkable, as well as being unfortunate. But perhaps we can contribute to turning these things around and putting these important subjects back into the center of mathematical discourse, which is where they ought to be. And what about Euclid, who wasn't on my list? Well, Euclid also studied the sphere, but for him, the sphere was really the place where the Platonic solids lived. And he was very interested in the 5 Platonic solids: the tetrahedron, cube, octahedron, icosahedron, and dodecahedron. And the point of them is that they can all be inscribed in a sphere. So the geometry of the sphere and the geometry of these solids are naturally connected. I suppose the Euclidean contribution is more in terms of the fundamental postulates for planar geometry, and then the subsequent development of people asking, well, how do these postulates fit spherical geometry? In Euclid's planar geometry, there were 5 postulates, or things that he took for granted. And these are very important foundational pieces for geometry. And because Euclid's Elements was so universally studied and admired, it was really a motivator for non-Euclidean geometry. Non-Euclidean geometry was built with a reference to Euclidean geometry. and particularly these 5 postulates. Let's just quickly remind you what they are. The first postulate is that if you have 2 points A and B and they're distinct, then there's a line that passes through them. In fact, there's one line that passes through them. The second is that if you have a line, which for Euclid was always some finite thing that you drew on a piece of paper, then that line can be extended. You can always extend a line in either direction to make it a longer line. The third postulate is that you can draw circles about any point with any radius. So you give me a point, you give me a radius, I can draw a circle with center that point with that as the radius. The fourth postulate says that all right angles are the same. Well, so there's a notion of perpendicularity. Okay, and that's maybe not entirely clear what that is exactly, but geometrically and intuitively it's pretty clear. So there's a right angle, there's another right angle. And Euclid says that all right angles are equal. By that he means that we can move one such configuration on top of another configuration by a motion. And the fifth, the most famous and controversial postulate, is that if you have any line and any point not on the line, then there's exactly one other line that passes through that point which is parallel to the given line. That's the parallel postulate. And parallel means that the two lines don't meet even if you extend them indefinitely, as much as you want. They never meet. So it's very natural, if you've been studying these things a lot, and then you come to a sphere, to ask, well, do these postulates hold for a sphere? Is it true that if you have any 2 points, that there's always only one line that connects them? Given a point and a radius, can you always draw a circle with the center that point and the given radius? Do we have notions of perpendicular lines? And do all perpendicular lines look the same? Is there something of a parallel postulate? If you have a line and a point not on the line, can you draw a parallel line to the given one through that point? So let's answer these questions. First of all, given 2 points A and B, can we find a unique line that passes through them? So for example, here it's A and B. Remember, a line for us means a great circle. And that's really the intersection of the sphere with the plane passing through the origin. And yes, we can do that. And the way we do it is we look at the 3 points A, B, and the origin. Those are 3 points. And then there's a unique plane that passes through them. So if we take the plane that passes through A, B, and O, that plane will cut the sphere in a great circle. And that circle will be a line through A and B. So the answer is yes, but there is a special case where it doesn't quite work so easily. The special case is when the 2 points are in fact antipodal, when B happens to be A bar. So suppose that one point is here and the other point is here, and these are antipodal points. In that case, the 3 points A bar, O, and A are actually on a line. And then there's not just one plane that passes through that line, there's an infinite number of planes. And that corresponds to then the fact that there are an infinite number of great circles that pass through the 2 antipodal points. In fact, we saw that in the earlier picture. If we choose the North Pole and the South Pole, then all the lines of longitude are great circles which pass through the 2 points. So there are lines, but they are not unique if A and B are antipodal. So there's a bit of a qualification there arising to the existence of antipodal points. How about the second postulate, that any finite line can be extended? Well, if you have any line, for example the line from A to B, you can extend that line. You can continue the line on in either direction. But of course, if you do keep on extending it, it will eventually meet itself again. So in some sense it's true that you can still extend it, but it's not the same kind of extension that happens in the Euclidean plane, where you just keep going further and further away. Here you end up wrapping around and around the same line. What about a circle? Can we construct a circle at any point of any radius? So for example, say at the point A, we can draw little circles, bigger circles, bigger circles. Eventually the circle will be an equator. And then if we keep going, the circles become smaller and smaller and become ultimately a point. Let's have a look here. So there's a point A. So what do circles centered at A look like? Well, a circle like this will be obtained by taking a plane which is actually parallel to the tangent plane here. All right, so if we look at the tangent plane and then another plane which is parallel to that, it's going to slice the sphere in a circle centered at A. So then if we move that slicing plane over, well, at some point we get the equator that sort of has A as a north pole or south pole. And then if we keep moving over, then the circles start becoming smaller on the other side until at the extreme case we'll just end up with the antipodal point A bar. So that's the range of circles centered at A. So how to answer this question? Can we construct a circle of any radius about any point? Well, yes and no. The circles that we're getting are of limited size because they all fit on the sphere. But nevertheless, there is some legitimate sense in which you can construct a circle of any radius. For example, suppose that the sphere itself was roughly a foot in diameter, and I wanted to create a circle centered at A of radius 3 feet. Well, one thing I could do is I could say, all right, let's start at A, let's choose a direction, say along that line, and then you walk along this line a total distance of 3 feet. So you're going to walk along this great circle, and of course you're going to come around to where you started. Maybe you'll go around several times if the distance is large, but you'll end up at some point. Let's say it's a distance of 10 feet, make it a little bit more extreme. So then you're going around the circle a couple of times and eventually you've walked 10 feet. So that means that you might actually be relatively close to A, but still you're at a distance of A in some sense. And then if you look at all the various directions that you could possibly have gone from A and do that same construction in all those directions, you would end up with a circle around A, which in some sense you could call that's the circle of radius 10 around A. So it's a matter of interpretation, but perhaps this postulate also holds. Perpendicular lines. Well, we'll talk about perpendicularity a little bit more later on, but perpendicular lines make sense on a sphere, and any pair of perpendicular lines may be rotated to any other pair. So this postulate, in fact, does work also for spherical geometry. It's the fifth postulate which definitely does not work. If you have a line, say this line through A and B, and you have any other point, then any other line through that other point will necessarily intersect the great circle you started with. So any two great circles on a sphere will intersect at 2 points, in fact. And the reason for that is, remember, a great circle is really the intersection with a plane. So if we have two planes both passing through the origin, then those two planes actually meet along a line. One plane in this direction, one plane in this direction, they meet along the line. That line passes through the origin. That line will also meet the sphere in 2 points. And those 2 points where it meets will be common to both great circles. So there's no avoiding the fact that there are no parallel lines, at least in the usual sense, on a sphere. So in conclusion, the first 4 postulates kind of work. The fifth doesn't. But the first postulate really has a problem for the special case when antipodal points are discussed. But other than that, you could argue that all the four postulates of Euclidean geometry hold in spherical geometry too. Definitely not the fifth one, and the first one, no, this special case has to somehow be excluded. This problem of antipodal points ultimately gave rise to a new kind of geometry. It's very closely related to spherical geometry, and one might say that it's almost a child of spherical and projective geometries. It was introduced by Felix Klein, a very important German mathematician, around the year 1870. And what Klein said is, let's have a look at the sphere, let's have a look at this problem of antipodal points, and let's get rid of this problem by doing something very imaginative. Let's identify antipodal points. Let's consider a pair of antipodal points as one object. So we're going to create a new space by identifying antipodal points A and A bar on a sphere S. So the objects of this new elliptic geometry are not points like they are on the sphere, but rather pairs of points and pairs of antipodal points. So here's a point A, and here's the antipodal point on the opposite side. The line joining them goes through the center. So we're now going to consider this pair of points as being a new object. And maybe to make it simpler to visualize that, maybe we could just join those pair of points by a rod. And then that rod is actually the new element of this new geometry. Here's another pair of antipodal points, B and B bar. So the rod that joins them passes through the origin. That's another element in this new geometry. And so we see that the elements of this new geometry can also be thought of as just being all these rods that are passing through the origin. And that's really essentially the same as the projective plane, because the projective plane is just all the lines in three-dimensional space which are passing through the origin. So elliptic geometry is somehow a combination of projective geometry, but we want to think of the geometry as actually still being related to the sphere. So we want to do measurements on these rods, taking into consideration that they're really representing points on the sphere. So we're going to use the metrical spherical structure to talk about measurement on the sphere, or on this elliptic geometry. So Klein's motivation for this is that now we can get rid of that ambiguity in the first postulate. Now if we consider these more general objects, then there's exactly one line that passes through any two distinct points in the elliptic space. For example, this is one point in the elliptic space, this is another point in the elliptic space. There will then be only one line that passes through them both, namely the great circle that they have in common. Because this device excludes the possibility that we're considering A and its antipodal point as two different points. They're no longer allowed to be different because they're glued to the hip. So this is elliptic geometry, and it's going to be a sister geometry to hyperbolic geometry. So Klein realized that elliptic geometry and hyperbolic geometry, and he was the one who gave names for both of those geometries, were very closely connected and somehow two sides of some kind of coin. We're going to see that these two geometries are very, very parallel to each other. They really are sister geometries. Let's have now a look at measurement in spherical and elliptic geometries, which classically are intimately connected with the idea of an angle. And that comes again from the history, the connections with astronomy, where the uniform motion of the Earth more or less forces angles upon us. So the ancients said, well, let's have a look. We have 2 points A and B on a sphere, or maybe we'll just look on a circle. You can think of this as being the great circle between A and B. How shall we measure the separation between A and B? Well, one idea is to look at the distance or the length of the arc, the circular arc between A and B. And that's intimately connected with the angle. If you double the angle, then the circular arc doubles. So there's a proportionality between the angle and the circular arc, and so we can say that that proportionality is essentially the radius. So if that's an angle alpha, we can say, we can define this distance to be r times alpha. So the spherical distance between A and B is r times alpha, where r is the radius of the circle. If we're in the elliptic case, and we have a pair of antipodal points and another pair of antipodal points, and we want to say, well, how far apart are they? Then it's a bit more complicated, because to go from one pair to another pair, we could say go from this point to that element, or we could go from this point to that element. And who's to say which one of those are better? Well, in this case, this angle is less than this angle, so it's probably reasonable to take the minimum of the two angles to determine the distance. So we can define the distance between these two antipodal pairs to be the minimum of this circular arc and this circular arc. However, there's another natural quantity floating around here, which is the Euclidean distance between A and B. After all, we're working in some two-dimensional or perhaps three-dimensional situation. We have 2 points. They might be on a sphere, but we can still talk about the distance between them, the regular, ordinary distance. That's going to be different from the circular length or the circular arc. It's going to be less, because that straight line distance is going to be less than this one. It's also going to be proportional to the radius. And the ancients thought in terms of introducing sort of a function of the angle. And I'll write it this way. I'll say that this is r times the chord of alpha. So if that's alpha, then this length is r times the chord of alpha. And as alpha increases, well, then this chord of alpha will also increase. This is a circular function, but it's not a very commonly used one these days. These days we prefer to think in terms of sines and cosines. So a student of mathematics these days would rather drop a perpendicular here and say, well, half of this chord is r times the sine of half of the angle. So the r, what we're calling r times the chord, is really 2 times r times the sine of half the angle. But the ancients took a while to come around to the notion of sine, and they preferred, at least initially, to work with this concept of chord. And you can hardly blame them. It seems quite a reasonable thing to do. You've got 2 points, you're just looking at the distance between them. That's an obviously interesting and natural thing to look at. So it turns out that when you're doing spherical geometry, although you can define the distance between 2 points on the sphere in terms of a circular arc, it turns out that mathematically that does not get you very far. It may be good psychologically, but when it actually comes to computations, it doesn't help you very much. You need to deal with these chords, or something analogous to it. And so the ancients had to create tables, because there's no easy way of going from an angle to a chord. So here's the picture. There's the center, there's an angle alpha, you've got 2 points. Then this straight line distance is essentially the chord. Okay, there's a factor of r, the radius. Okay, but so the question is, given alpha, how long is that chord? And you had to compute that. And there were various clever ways of computing it for different values of alpha. There was no easy formula for it. So the ancients made tables. Half a degree corresponds to a chord of this value. 1 degree corresponds to a chord of this value. 1.5 degrees, a chord of this value, and so on. They tabulated long lists, and these were fundamental tables. So one of the famous ones occurs in Ptolemy's Almagest, created around 200-300 years AD. It was one of the best tables at that time, and it was used subsequently by the Indians and the Arabs. So it's very influential work, this Almagest. In fact, the word Almagest is actually an Arab word. It was studied very intensively by the Arabs. An interesting feature is that in this table here, base 60 is used, so going back to the Babylonian number system. And another interesting thing is that the radius was rather chosen not to be 1, as you might think these days, but rather 60. That meant that the numbers involved here were not so small as they would be if this was a radius 1 story. This is radius 1, and that's 1 degree, then that chord becomes a very small number. But with r equals 60, it's somewhat more manageable. So this is here in sexagesimal. It's base 60, and it's working with radius r equals 60. Then, many hundreds of years later, in the Indian period, we have a lot of Indians who took on this problem and developed other ways of thinking about things. In particular, they introduced the sine function. So where we have the angle alpha here, and then in terms of computing, we don't compute this chord length so much. We want to compute rather this perpendicular distance. So r times sine alpha, that's that quantity there. And then there are again tables for angles and the values of r sine alpha. And we have a number of prominent Indian mathematicians. There were more. And this is the kind of thing that they produced. They used a value of r equals 120, as well as some other values. And the values of the angles here are a little bit curious. Again, it was computationally efficient for them to choose certain values. Later on, the Arabs took these tables and further modified, made them more accurate. So for a long time, tables associated to circular functions, be they chords or sines or cosines or various other variants, were absolutely critical in making computations in spherical geometry. And even relatively recently, if you were a Napoleonic sea captain, you would have tables of sines and cosines that you would use to make computations having to do with navigation. These would be very valuable to you, and every captain would have to learn how to use those. So it's only relatively recently that the calculators have sort of superseded these tables. One of the very interesting aspects of this approach that I'm going to be proposing, which is an alternative to all of this, will be that it will remove the need for tables. So I'm going to present to you with a new way of thinking about spherical trigonometry that's going to be much simpler than the one that the ancients used, much simpler than the one that's used today. And it completely eliminates the use of tables. So it should be of immediate interest to anybody in this area. It's a very big claim. You'll see that it actually does work. So to give you a sense of why we need these chords or sine functions and why we can't just deal with the distances on the sphere themselves, let's have a look at a very important classical result. This is Menelaus's theorem, which was a key theorem in spherical trigonometry. You're probably mostly familiar with the planar case. These days, this is what students learn. So let's just have a look at the planar case first. We have a triangle, A1, A2, A3, and we have another line that cuts the triangle in 3 more points, B1, B2, and B3. Menelaus's theorem tells us something about the relationships between the various lengths formed by these new points and the original 3 points of the triangle. So it's kind of organized cyclically. The distance between A1 and B3 divided by the distance between A2 and B3. So this ratio divided by this ratio, multiplied by A2, B1, this ratio to this ratio, multiplied by A3B2 to A1B2, this ratio to this ratio, is equal to 1. The planar version was not, in fact, the first version of this theorem. The first version actually was introduced by Menelaus in the spherical context. So he wrote a book called Spherix. In fact, many ancient Greeks wrote books called Spherix. It was a very popular title for books. And in his Spherix book, which is a very good book, this theorem appeared. So this is a sphere, and in analogy to here, we have a spherical triangle, A1, A2, A3. So there's one line, there's another line, there's another line. That's our basic triangle. And then we have one more line, analogous to this one, which is this line here, which meets the original triangle in points B1, B2, and B3. The radius of the sphere is r. And what we're going to do is we're going to measure distances in terms of these angles. So this is just our convention, our notation. If we have 2 points on the sphere B2 and A3, let's say, there's the center of the sphere. The angle formed by the ray OB2 and OA3, that angle alpha there, we'll denote it with this little symbol, all right, B2, A3 bar. That represents that angle. So if we multiply that by r, then we'll have the spherical distance between B2 and A3. So up to the factor of the radius, this is essentially the spherical distance between here and here. So you might hope that you just take this formula and you replace these Euclidean distances with the spherical distances. And maybe that would be the spherical version. But it doesn't work so simply. If it worked like that, well, then angles would be much more effective in spherical trigonometry. But unfortunately, it doesn't work that way. Here is the form of Menelaus' theorem. What you need to do is you need to take this angle, say A1, B3, and you multiply it by 2 and take its chord. So what you can think there is you're doubling that angle, or doubling that distance, and then taking the Euclidean distances between those 2 points. So it's not just the Euclidean distance between A1 and B3. We have to double the angle first and then take the Euclidean distance. That's what's happening here. Otherwise, the terms are exactly analogous to these ones over here. We have chord of 2A1B3 over chord of 2A2B3 and so on. And when we multiply these all together, we get 1. So you can see why the tables of chords or signs was crucial, because the distances along the spheres themselves don't suffice to make calculations. You need the chords or some kind of trigonometric ratio. These days, we would write this rather in terms of sines. So we would say, well, this is just the sine of this angle divided by the sine of this angle. It amounts to the same thing. But in Menelaus' time, the chord was seen as a more natural thing than the sine. The ancient Indians then would have transformed this into a law involving sines, and the Arabs as well. Okay, so next time we are going to have a look at some other classical aspects of the sphere, going back to Archimedes, and then a more recent one going back to Harriot in the 17th century. And we're going to be talking about areas and volumes on a sphere. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.